today I'm going to review of the chaotic search experiment here in Japan. Mainly today I want to discuss the inclusive spectra, not the coincidence spectra. Starting from the KKPSE 548, Kishimoto-san's measurement on the carbon 12 K-PN reaction, and recent JPAC experiment on the E05 carbon 12 K-P measurement, and the E27 and E15 for those reactions. And I briefly discuss the coincidence spectrum too, and summarize my talk. Yeah, we still believe the strangeness should play an important role in the high density hadronic matter, especially realized in the inside of the core of the neutron star. And we hope the next neutron star binary merger event to occur in not so soon, and which will give us precious information on the equation of state of such a high density matter. Okay. Okay. So Kishimoto-san first suggested the K- nucleon reaction to search for the K-bar nuclear bound state system with K- being at 1 GeV over C. And his idea was very naive, then just putting the K- onto the nucleus and kicked out one nucleon in the forward direction. Then the K- or the K-bar is left as a chaotic nuclear system. Then he got this spectrum on carbon 12 K- neutron and carbon 12 K- proton. And as I mentioned, in the left-hand side, you see the elementary process cross-sections as a function of the incident K- momentum, so that at 1 GeV over C, we have a resonance of the lambda star 1800, which gives us this huge cross section at 1 GeV over C. So that's the momentum Kishimoto-san selected. And he got this missing mass spectrum in the K- proton and K- neutron. But then there is a problem, as suggested by Orokyo and Vincent Magas and those people, theoreticians. This is not really the inclusive spectrum, but semi-inclusive spectrum. To measure the velocity of the forward proton and neutron, they need to measure the time of flight of those particles in the forward direction with a path length about 10 meters. So for this measurement, they needed the start timing of the prompt reaction to occur in this K- nucleon reaction. So to get this prompt timing, they put the additional counters for the surrounding the target to get the prompt reaction timing. But as Orokyo and the company claimed, this is not unbiased, but still we have some bias for the missing mass spectrum by requiring this prompt reaction timing. That is shown in this picture right-hand side. The red curve corresponds to the case for the 60 MeV deep potential case, and the blue dashed line corresponding to the 200 MeV potential case. But if we require such a prompt reaction, then those two peaks are gone, and what's left is this green dashed line and small dashed black dashed points. As you can see, those green curve and black dotted curves, the shape are quite similar, and we have no sensitivity to discriminate these 60 MeV potential and 200 MeV potential, which should be different from the physics point of view. But as you see here, because of this prompt bias, prompt coincidence bias, it's not separable. So that those theoreticians made a caution to interpret this spectrum as a signal for the bound state existence. But there should be other factors you should keep in mind. As I said, this 1 GeV over C is at the S channel resonance of lambda star 1800, and which decays into K bar N in the case of elastic scattering. And also we have sigma star pi decay mode or the nucleon K star decay mode and so on with around 10% branching fractions. And the 5 millibar steradian is the total production cross-section of this S-channel resonance. So that we, in the K minus P, we have a quasi-elastic K bar N, K bar reaction. And also we have one body absorption reaction K bar N going to pi sigma or pi lambda. And also in the case of the multi-nucleon nucleus, there should be 2 nucleon absorption process with some fraction. So in the K minus P missing mass spectrum in the forward, all of those 3 reactions, if we got a high energy of nucleons, those are the overlap in the obtained spectrum. So that we should be careful about also which reaction processes are producing each spectrum. So that's one of the important point with the K minus P reaction. Actually, the one body absorption process, K bar N to pi sigma, this reaction mode was so far no measurement took place for this reaction. Only the K bar N, and maybe some 2 nucleon absorption processes. Those we know already, but in the middle part of the one body absorption shape, we don't know. No measurement at all. Okay, so then we had the E05 experiment. That was the main purpose was to carry out a K minus K plus reaction for the cascade hypernucleus. But at the same time, we did the measurement of the carbon 12 K minus proton reaction at 1.8 GeV over C. So this is a really the inclusive measurement of the proton, because we don't use the time of flight for the proton energy measurement, but we use the magnetic spectrometer system. So we don't have any bias coming from the coincidence. No coincidence is required, just a forward proton. And instant momentum was a little bit higher than the Kishimoto's measurement, but the momentum transfer is shown here on the right. And as you see, the momentum transfer value are not so different with two different incident momenta. So, and this is the experimental setup. We have a beam momentum spectrometer system and SKS for the forward proton spectrum. So 4.2 MeV is the missing mass spectrum, so it's very good, and no bias is required for the target region. Just forward-going protons are measured. And this is, we took that data for the hydrogen and also carbon. And this is the case for the hydrogen, and the K minus is reaction. And we have a very good separation of the K bar N reaction. And also we have K bar N to lambda pi and sigma pi component in the forward direction. Also, we have the K star neutron nucleon reaction, that is the blue dashed line. And this is the obtained quasi-free K bar N K minus P inclusive spectrum at 1.8 GeV over C. The black dotted lines are our data. Because of the just no bias measuring that the proton in the forward, we have a very high statistics and very smooth spectrum shape. And the green dotted line should be the quasi-free K bar N component. And by comparing this to the experimental data, the experimental data is somehow shifted to the left-hand side. And what I would like to note you is the tail part in the bound region, and 0 to 100 MeV, we have a clear tail in the bound system. And this reminds me the semi-inclusive neutron spectrum taken in the E15 experiment on helium-3 target. the K minus going to neutron in the forward direction. This is in the middle, and on the top, I put again the E05 K minus proton inclusive spectra. By comparing these two spectra, you see below the binding threshold, we definitely see the tail, very similar tail component in between helium-3 and carbon-12. The difference of the Fermi momentum just make the difference of the distribution of the quasi-free K bar and peak structure, but it's quite a similar spectrum, and especially in the bound region, the very similar structure are observed, as you see here. And this again reminds me that the theoretical calculations, this is in the linear scale, so that the K bar N cross sections and this tail part, the height was at the threshold. It's very say 1:3 or 1:4 ratio. So it's in the same order, not less than 10%. And in such a case, then I remember the Koike-san and Harada-san's theoretical calculations by using the various potential depths, 20 MeV, 40 MeV, 70 MeV, etc. But all those calculated spectrum tells us the peak at the K bar N quasi-free component, and at the threshold, we have 1:2 or 1:4 ratio. So it's the very the same order of magnitude. So in that sense, this theoretical calculation and experimental data suggesting the very similar spectrum shape. Only the maybe in the experiment, because of the larger imaginary part compared to the theoretical calculation, it's smeared out as a tail. But anyway, it's very similar shape with the theoretical calculations, I think. And even if,
10 minutes.
Yeah, 10 minutes, okay. So this is the Koike Harada's calculation for the coincidence case. But anyway, even in the coincidence spectrum, the magnitude is almost the same. That's an important point. And from the shape of the these binding energy, K-on energy, 50 to minus 100 MeV, the centroid of this black dotted lines, we made a fitting for the so-called Morimatsu-Yazaki Green's function method analysis. And we get about 80 MeV, minus 80 MeV for the real part, and minus 40 MeV for the imaginary part. We get a quite reasonably good fitting with the green dashed line. That's corresponding to the minus 80 MeV. But and the left-hand side is a linear scale, and the right-hand side is a logarithmic scale. And in the logarithmic scale, you notice that below the 100 MeV, we had a very large disagreement between the theoretical calculation and our inclusive data. So that could be some hint of the called deeply bound system. So by taking, say, one Bright-Wigner form in around 100 MeV, this enhancement tells us the binding energy about 90 MeV and width 100 MeV. So that this could be the two nucleon absorption processes. Okay, so I should say. So as I said, in the K-P reaction, I think we have two components. One is K bar N quasi-free reaction, and going to the K bar nucleus bound state, which is not so deep, 30 to 40 MeV binding energy. But in addition, we will have lambda star quasi-free production, which is not separated in this picture, I mean E05 data, but the quasi-free lambda star, part of the lambda star going to the deeply bound component, so that that makes the component at 95 MeV. So that's our idea, and that is in the E27. This is a pi K reaction on deuterium, and lambda star is quasi-freely produced. And this is, in this case, we have no K minus component. K bar N component is not produced in this reaction, so that lambda, sigma, and Y star are produced quasi-freely. And what we observed in this reaction was 30 MeV shift in the Y star, lambda star. So maybe this is just a quasi-free lambda star production, but we could have some component here, the bound system of the Y star P.
Okay, 5 minutes left.
Yeah, okay. I'll come to the conclusion. And so my final comment on the E15 experiment at JPAC is here. They claim the observation of the bound state of the lambda P state, lambda P K minus PP as shown here in the red curve, and get the production cross section about 10 microbarn per times the lambda P branching ratio. And this is a very small number. And what they claim is the compactness of the K minus PP system. But this should be a little bit, I think we should make some cautious on this compactness of the K-minus PP. Okay, so I come to my summary. I showed you the inclusive spectrum in the E05. The real inclusive spectrum is obtained for the first time on the carbon target, and this fitting value was -80 and -40 MeV, and same kind of shape was obtained even for the semi-inclusive spectrum in the E548 and E15 neutron spectrum. A tail in the bound region was observed, and that was consistent with E05 and the theoretical calculation. So a bound state, but broad state exists in the K-P sigma spectrum. But then the theoretical calculation suggests that that component should have a large cross-section, as large as quasi-free K bar N component. And that is not observed yet. And I didn't have enough time for the coincidence spectrum, but probably in the 27 case, we have a lambda star 1405 and a proton bound state in E27, and the E15 is a very small fraction of inclusive cross-section. Thank you very much.
Thank you very much for your showing the nice data from the E05 experiment. Okay, it's a time to your question and comment. Professor Offset, go ahead.
Okay, thank you. I don't know that I had raised the hand, but it looks like a couple of questions or comments. You know, the first, I mean, let's see. I mean, when you talk about Koike and Harada, I think it's page 11. Yeah. Can you go there? I mean, to page 11, because I mean, I think one can make a comment here because it looks. Yes, well, Koike and Harada. I mean, there's another.
This one.
Yeah, that's fine. That's fine. That's fine. That's fine. So, you know, I mean, they predict there, I mean, a beautiful peak, right? They are in the, at 115 D. On the right figure, on the right, number D. They predict there was last peak, and then there is another peak, which I presume will be due to some deeply bound chaos atom, right?
Yeah.
But it looks like in your experiment, you don't see anything like that. Is that also correct?
Yeah, it's correct. So
very good. Okay, so that's the comment I wanted to say. I mean, that nature doesn't want this very high, very deep bound states. Okay, good.
Yeah, that's not the case.
Very good, excellent. Yeah, and now I mean, going back, I mean, to the E15, the last thing you talked about. I was surprised, and I mean, I have heard that also, you know, I mean, about the compactness, you know, this K minus PP bound state. I never understood, I mean, the arguments, I mean, the experimental arguments for this compactness. I don't know where it comes from. I mean, they say that's a compact object, but I never understood the reasons. I presume it is simply because Yamazaki has told them, I mean, that it should be compact, you know, I mean, remembering the times when he was compressing matter by 10 to 10 times, I mean, nuclear matter density, the great old days. But I mean, the fact is that, I mean, I don't know any reason, you know, experimental reason or argument that tells me that it should be compact.
Yeah, they...
Go ahead.
In the fit with the binding energy of 42 MeV and with 100 MeV, they brought some form factor for the production of this K-PP object. And this form factor value is rather large.
Yeah, but you see,
so
I mean,
that's argument of the compactness.
Very weak argument because, you know, I mean, and Ramos, I mean, they also explain that, I mean, theoretically with a good theory, they get, I mean, less binding, and also the width, I mean, is also a little smaller. And the cross section that they get, I mean, is just perfect. So, I mean, then the argument is very weak. because you can get that without, I mean, assuming, making these assumptions.
Yeah, yeah, I agree. I mean, that these cross sections should be order of 100 microbarn or so.
Okay, I finished. Thank you.
So compared to that, this result is too small.
Okay, so please discuss with the next speaker, Masa. Okay, let's move on to the next speaker, Professor Iwasaki from Riken.
All right.
And you have 30 minutes, including a discussion time. Okay, go ahead.
Okay. Can you see the slide?
Yeah, perfect.
Okay, thank you for let me talk about the title. Under the title "Experimental Study Towards Spin Parity Assignment of the Fast Chaotic Nuclear Bound State" (ABP). So I'd like to talk. Well, I just remind you what we have done. At JPAC E15, we have observed K-PP clearly in the exclusive non-mesonic reaction channel, K- plus helium-3 going to lambda P plus N. And in here, in the E15, we focus on the simplest final state. Going have lambda, proton, and neutron. And we plotted the event as Nagai-san explained to you, like for momenta, mass and momentum transfer to the lambda P system. And only in lambda P invariant mass, we have anomaly, kinematical anomaly shown in the spectra. This is again what Nagai-san explained to you, and I just wish to skip all the detail of the E15 experiment, and we see clearly see a signal at this region, and the momentum slice, the spectrum is shown here, and this is a binding threshold for K1 to proton is located in here, and the clear peak observed well below the mass threshold of MKPP, indicated as a dashed line. And this is the mass slice at the region of interest, and this is what Offset-san and Nagai-san are discussing about. We interpret our data based on simple PWIA, having mass term and momentum transfer term, and we simply convert this momentum transfer parameter to the mass, to the size of the system, and taking into account that this can be represented in the harmonic oscillator model. This can be very small, but this is not a simple picture. But anyway, what we observed very clear signal, and today I'd like to talk about how we can this part. There could be many experimental program, but today I'd like to focus on this. Now, the spin parity JP is the most fundamental quantum number need to be examined experimentally. And this JP defines internal structure of K bar and then bound state. Now, there are two candidates as for the K bar and then ground state, in which NN symmetry and K bar couplings are different. Namely, for JP 0 minus case and JP 1 minus case. For nucleon is fermion, so it should be asymmetric as a whole. And the difference is whether isospin part is symmetric or spin part is symmetric. So for isospin or PN is symmetric part, it can be written like that. And for JP 0 minus system, the coupling between K bar and N for isospin 0 channel is 3 times bigger than that of isospin 1 component. So it is expected to be very deep, and this is should be rather shallow. More specific representation of such a system is I simply take this part, but it is not simple like as I described. The strength of isospin 0 component and 1 can, this more specific representation, it should be the JP 0 minus should be represented in this way. And the isospin 0 or 1 can be evaluated like that. So this is, and I'd like to discuss whether this or that is realized in the, or what is the signal we found in E15, how to clarify which is the real case. And in today's discussion, let me discuss about how to access JP by the K-BP going to lambda p decay is the question. For J equals 0, it means no angular correlation is a question. I mean, we wish to study the lambda p decay mode in detail using its spin. For both lambda and proton is positive, parity is positive. So to have minus parity in the final state, the angular momentum should be 1. This is saying for JP equal 1 minus case, it should be 1. And to be J equals 0, this side, it must be spin of lambda p system must be 1. And indeed, for this spin must cancel the angular momentum of lambda p in the final state. So in the final state, lambda p spin must be parallel in this channel. On contrary, the JP 1 minus is a bit complicated. To form J equal 1, it can spin can be 0 or 1. Right? And for this side, proton spin and lambda spin is anti-parallel, and this is just simply uniformly spin must be uniformly distributed. On the contrary, this spin lambda p spin equal to 1 to be 1 minus in total. Angular momentum and the spin direction must be orthogonal. This is the summary of distribution of spin and decay axis for k by n for Jp equal to 0 minus and 1 minus. This is special distribution of spin. This is the KPP decay axis, and I plotted the spin direction like this way. And the same quantity can be described as a function of cosine theta, where this theta is the decay axis and the angle between decay axis and spin axis. So in this case, both lambda and proton is mostly orthogonal to the decay axis. On the contrary, the JP1 minus case is there is a uniform distributed part, which is spin anti-parallel, and the other part, 2/3, is mostly parallel to the decay axis, like that. And the branching ratio from of this one and that one is 1 to 2, and it results in the alpha, which is the whether lambda and proton is parallel or anti-parallel is we have average. In average, it will be 1/3. The spin, as I described, the spin distribution referring to the decay axis are quite different between the two. But the problem happens that the spin direction itself is not accessible by an experiment. So to know the JP, we need to study further about lambda p spin-spin correlation. Now, let me talk about how to measure lambda p spin-spin correlation. For that, we need for lambda case, it is quite easy. This is simply a weak decay, and this weak decay let us know where the lambda spin located. Proton emitted in the direction of lambda spin. For the opposite side, we have proton, and when we put carbon target here, for example, as a polarimeter, it will react asymmetric way, and so that we can measure the angular correlation between this phi. It can be written like that. And I'd like to describe how we're going to do in detail in the next slide. But anyway, as I described, the lambda spin is quite relatively easy to define. And this is well-known formula. And asymmetry of lambda is rather large, 0.73. And for relative to the spin, it's a proton direction dispute like this. And this is uniform in phi direction. So is just a schematical plot of how the decay looks like. Now, this is the PC nuclear scattering asymmetry, and it's also written in the same formula, but this is actually actual asymmetry can be obtained experimentally. This is actually the same plot. This is horizontal scale in this one is X scattering angle, and this is the Y scattering angle. When we put proton in this direction, the perpendicular to the screen, having spin upwards, then left-hand side scattering is much bigger than the right-hand side. So we can know the spin direction of proton. And let me describe the analyzing power of proton spin. This is well known and well examined. And the analyzing power of proton spin have a maximum around 0.2 GeV in kinetic energy, as you see here. And so what we wish to do is to measure this proton, and the kinetic energy of this proton in lab flying is plotted like that. And well, it is a little bit lower than the optimal value here, but one can do it in experimental in an experiment. No. So the this is experiment setup we are thinking of. We wish to build a large-scale solenoidal spectrometer, and after this large solid angle cylindrical drift system, now we wish to place a stack of polarimeter tracker behind this cylindrical detector system to know the proton kick on polarimeter. Now, let me describe how we can have this asymmetric parameter as a function of phi in the experiment. This is simply a lambda decay formula, and this is the scattering part of the proton on carbon target. And what we can measure is proton scattering asymmetry, which must be orthogonal to the proton motional vector. And we have a decay axis like that, and actual spin may be distributed all over the sphere. And this side, from here to the opening angle between here to there is a problem. This and this angle is from here to there, and this is for this part. This sine lambda theta is the asymmetry effective polarization of this spin. So it can be described like that, and you can compute all the term and integrate that over all the sphere. And it is rather difficult to obtain result, but most of the time, cross term is cancelled out, and especially when the spin distribution S is uniform in the phi direction, the result is coming to like that. And if spin is also uniform in theta direction, the result is written like this. The expected asymmetry is relatively small, but sufficient for dedicated experimental setup. And this is the number for that. And please note that the most important part of this convolution is this. The asymmetry, effective asymmetry, is proportional to sine square of this angle. Now,
10 minutes left.
okay, this is lambda p bare asymmetry. Just compare the reaction and the decay. This is a simulation-based calculation for JP equals 0 minus, and this is 1 minus, and horizontal scale is just the normalized like that, and the vertical is bare asymmetry, described like that, and this is the angle between lambda and proton in phi. So this asymmetry seems to be so much different. This difference helps to discriminate if the state is 0 minus or 1 minus. So what is the origin of this discrepancy? There is two reasons. One is asymmetry canceling happens on polarimeter. In fact, in an experiment. And the other is the effect of asymmetry is sine squared. Well, maybe for JP is 0 minus, only parallel happens. And for JP equal to 1 minus, lambda p can be parallel or anti-parallel. And the asymmetry canceled on this scattering angle. Maybe the situation can be illustrated by graphically. This is again the decay angle from motional vector and spin for JP 0 minus or 1 minus. And it depends on magnetic field and also the momentum transfer. But anyway, the global shape is same as we described in my talk. And when we overlay the effective asymmetry on the same figure, the weighted yield is like that. So for 0 minus, it is easy to measure the spin, but for 1 minus case, these parts are dropped. And the ratio of 2 to 1 is already violated in this effective asymmetry. So that is the situation. And another thing I'd like to discuss is how to calibrate the alpha, the absolute value of alpha lambda p. For that, again, just an illustration that this is our experimental setup we are thinking of, and what we wish to measure whether this proton and lambda is parallel or anti-parallel. But like we can measure the spin asymmetry here and the decay, and same thing can be done for this proton as well. And lambda and proton, because it's simply weak decay, the spin is identical from lambda and proton. It is ensured. So very simple-minded manner, we can compare this part and this part, like, and for that comparison, we have bare symmetry here as we described like that, and we can calibrate it using Proton from lambda decay asymmetry. Then everything is canceled out so that we can plot alpha directly, and there must be a correction factor which can be evaluated simulation in detail, and especially for JP1 minus case, correction factor is small, as small as 2% in such a case. And, okay. Okay. So I believe we can measure the alpha lambda p in a good manner to discriminate these states with small correction factor, and this is what I'd like to summarize my talk today. And there's many experimental study we can do in future at JPAC. So that's all what I wish to say. And please join if you can think this is quite interesting to do. Thank you very much for your attention.
Thank you very much for the impressive idea for the spin parity determination for the KPP. So there it's open time for discussion, question or comment. Please raise your hand or monitor or directly speaking by unmuting your mic. Okay, Laura.
Hi, impressive talk and really brilliant idea, Masa. Thanks for this talk. I have a question about the possibility of having the measurement with polarized targets. Whether you have considered these as an help to select the spin final state, or whether this is completely not useful for your purpose.
Well, that's a good suggestion. Well, actually, sorry. But as I described, that we believe sorry, where is the? We believe that this might be the realistic ground state, and even if we polarize the target, once it comes to be JP 0 minus, then you can, or maybe the kicker out neutron might be polarized in that case, but this is just a spherical, unfortunately. That's why we did.
I see. And so since when are you going to have this measurement that you propose? When is the data taking place?
Well, in principle, what we wish to do is what we have done for E15. So we'd like to do the only place what we can do this kind of experiment is JPark, unfortunately.
Yeah, sure.
And we have some difficulty to evaluate the beam time because well, it's roughly 2 months will be enough, or more than two months. It's very difficult to have beam time. And
Thank you.
Maybe we need a shortened beam line at the same place, or we need to request divider of K1.1 instead of K1.8 PR or something. We are working on it to finally evaluate the beam time. Thank you very much for your question.
Okay, thank
Okay. Is there any other short question or comment? No? Okay, thank you, Professor Iwasaki, Masa. Okay, let's move on to the next talk. The next speaker is Professor Chifuri. Okay, so you have 30 minutes. Okay, okay, please go ahead.
Hello, everybody.
Yeah, I can hear you. Please share your screen.
Looks I have some problems to put my
monitor. Okay.
I'm sorry.
Can you enlarge your window?
Okay.
Okay. Okay. Perfect.
Good. So I would like to start with thanking to the organizers for an opportunity to give a talk here. And here you see a short summary of my talk. And I would like to apologize also to those who have already seen my talk on the TEA seminars, because it's quite similar. In fact, I added just a few transparencies, but I hope the audience is partly different here. And so I really didn't have much time to prepare more. And so I will start with some short introduction. Then I will present you the chirally motivated K-bar N interactions, speak about the origin of dynamically generated resonances, poles, and discuss whether they are really one or two lambda 1405 poles. And in the end, you will see some new results we have with a new K-bar N model. So for the introduction, the lambda 1405 is really interesting hadron because it keeps our interest for more than 60 years. It was discovered or predicted by Dalitz and Tuan as a subthreshold resonance in the key metrics analysis of chi- proton data, and it was confirmed 2 years later in the P sigma mass spectra. And because lambda 1405 is much lighter than the lowest and star resonance and a potential spin orbit partner in lambda 1520, then it is very difficult to explain the structure of lambda 1405 within a standard constituted quark model. So we mostly speak about the hadronic molecule, which is loosely bound K-bar N state, or there are also some ideas that it might be a pentaquark state. But the most common interpretation is that it is really a K-bar N quasi-bound state, which is submerged in some kind of pi sigma continuum, and it is a result of coupled channels pi sigma K-bar N dynamics. And the current unitary coupled channel approaches, which are based on effective chiral Lagrangian, they generate two poles which can be assigned to lambda 1405, and it was first realized by Euler and Meissner already 20 years ago. And if you are more interested in lambda 1405, I would highly recommend you two reviews by Hyogo Do and Jido, and the most recent one by Maxime Mai. In this page, I show you two examples of pi sigma mass distributions in which lambda 1405 can be seen. In the first figure on the left, I put together three rather compatible results by Thomas, Hemingway from Bumble data, and more recent Anke collaboration results. They are these three bins that follow each other here, each energy, and you see that all three distributions are nicely comparable, and here you can see also some theoretical predictions taken from the work of myself and Smejkal, and the lines are here if one considers only one pole, or which is the K-bar N related for by dotted line, or by dashed line only the pi sigma related pole, and if one combines them, one can get slightly better reproduction of the experimental data. And here in these figures, I show the class data reproduction by Maxime Mai and Ulf Meissner in their work, and they are also some new experimental data on pi sigma distributions, which are more modern, and in different reactions you can see a bit different structures there. So from the theoretical point of view, we really see lambda 1405 as emerging due to coupled channel dynamics of meson octet with baryon octet, and so the chiral models describe this system, which involves the channels that are listed here, and they span quite a large interval of energies. It's something like 600 MeV, but we are most interested in the region about the K-bar N threshold. And in principle, one could add to the meson octet and baryon interactions also singlets and have eta n eta channels treated separately, but it was not done in the STRANGENESS -1 sector yet, but we did it already with Peter Bruns for the eta n interactions. But coming back to K-bar N system, we have strongly interacting multi-channel system, which has the S-wave resonance, the lambda 1405, just below the Chi- proton threshold. As I already said, the modern treatment is based on effective chiral Lagrangians, and this is done that the effective potentials which appear in these Lagrangians are constructed to match the chiral meson baryon amplitudes up to either leading order or even next to leading order. And then Lippmann-Schwinger equation or Bethe-Salpeter equation is used to sum the major part of the perturbation series. So this is how it works. In the schematic picture, we have the interactions that are considered in the chiral approaches. We have the Weinberg-Tomozawa leading term, which is really the major part of the interaction. Then we have the two Bohr terms responsible for direct and crossed interactions. And finally, we have corrections which appear at the next to leading order, and they contribute to the contact interactions. And the parameters of these models are meson decay constants, then axial vector couplings. This can be determined from other experimental data, but we have also couplings that contribute to the second order terms, and those are fitted to the experimental data. And this amplitude then is used as an effective potential to sum in the by Lippmann-Schwinger equation. And so we need additional parameters to regularize the meson-baryon loop function. And these are also fitted to the experimental data. Classically, one fits the low energy total cross sections with chi minus in the initial state interacting with proton, and here you can see the reproduction of the cross section for the channels that are open at the K-bar and threshold, including the cross section to chi 0 neutron channel. Then one also fits the threshold branching ratios. I mean the K-bar n threshold here. These are 3 threshold branching ratios and very precise data on cationic hydrogen, which concern the shift and energy width of the 1s level that are caused by the strong interaction. And in this figure, you see the results of 3 experiments, which are put here by as rectangles within one standard that showed the experimental result, which is in the center of the rectangle, and within one standard deviation, it forms the rectangle. And you see that the prediction of several chirally motivated models fit quite well the recent Siddhartha measurement, which is the most precise, and all these theoretical predictions provide really a good reproduction of the Siddhartha results, which was not quite so with relation to the previous year results. So then once we have the model with fitted parameters, we can generate the amplitude, we can study the S matrix, and we can make predictions for, we can look at the poles which are assigned to the lambda 1405 resonance. And this is shown in the left figure here, taken from the review by Hyodo and Jido. And you can see the pole which is couples more strongly to the K-bar N channel and is closer to the real axis, and it appears at energies about 1425 MeV. And then there is the second pole, which couples about, in some models about evenly to K-bar N channel and pi sigma channel, but in fact it's more related to the pi sigma channel, and it's more distant from the real axis, so the resonance is much broader with respect to pi sigma, and from this you get the illustrative picture that it is in fact something like a K-bar N bound state, which is submerged in the pi sigma continuum. And in the left figure, I show a result from another review by Maxim Mai, who collected all the predictions for these 2 pole positions, which appeared recently over the last 20 years. And here you can see that all the theoretical models are in a kind of agreement on this pole, which is related to K-bar N and closer to the real axis, but the experimental data and the theoretical models are not restrictive enough to provide a position for the second pole. So that's because the experimental, the second pole is not that much sensitive to the experimental data. And in this picture, you can see also some pole positions taken from phenomenological models that include only one pole, and then it is this pole. So where do the dynamically generated resonances or the poles come from? I will demonstrate it for the Prague approach, but it's more general that the amplitude has poles for complex energies in situation where the determinant of the inverse matrix is equal to 0. So if we write the determinant of the inverse matrix and set it to 0, then if this equation is satisfied, then we have a pole. And the origin of the poles can be traced to the so-called zero coupling limit, in which we switch completely the interchannel couplings. So we are left only with the couplings on the diagonal. And then this condition can be rewritten as a product of just one channel equations, let's say, which determine the pole positions. So we then can have a look at the position of the pole in just one channel and get this equation. That's the equation we get for the Prague model. This is the inverse of the potential, and this is the green function or loop function integral, which can be done algebraically in the Prague model. And you can see that only states with have non-zero diagonal coupling can satisfy this equation, and so can generate at the pole in the zero coupling limit. And then when we slowly switch on back the interaction and enter the interchannel dynamics, the pole moves, and it moves to its physical limit. But in the zero coupling limit, we see that the non-zero diagonal couplings are only if we consider the Weinberg-Tomozawa interactions and as the leading force, then we have the non-zero diagonal couplings in the channels by sigma, k bar n, and k cascade. So we should have 3 poles in the isoscalar sector and 3 poles in the isovector sector, but I do not speak about that now. And so these 3 poles, when we switch on the interaction, they evolve into the states we all observe in the physical limits, and the 2 of them are assigned to lambda 1405 and the third one to lambda 1670. And in general, the exact situation depends on the model. And in this picture, I show how the pole moves. The left figure, we have the isoscalar poles, and in the right figure, we have the isovector poles, which are also 3. And so this is the position of the k bar n related pole in the zero coupling limit. And when we switch gradually the interaction, it moves into the physical position. The pi sigma related pole does not move that much, and it generates much broader resonance. And this is for the lambda 1670 pole, or k cascade related pole. So we have 2 poles assigned to lambda 1405. And I personally believe that it's a good theoretical concept because, as I told you, we have 3 poles generated in the zero coupling limit. And so we have to assign them 3 poles in the physical limit. So we are left with 1 pole for lambda 1670. So the 2 remaining lines should be somewhere. And as far as one of them does not go too far from the real axis, it should also be there. And we are left with assigning it to lambda 1405. But this 2-pole idea of lambda 1405 was attacked recently by János Révai, and he presented quite good argument, I must say, and it's based on the fact that when we calculate the Lippmann-Schwinger equation, we normally in this second term in the integral, which includes the potential and the T matrix, do so-called on-shell factorization, where the loop momentum in the argument of the potential and the T matrix is set on the on-shell, and then these 2 quantities can be pulled out of the integral, and it is believed that it is equivalent to introducing Ted-pole contributions to the interaction kernel. And János Révai put this procedure under serious question and demonstrated that the pi sigma related pole disappears if the off-shell part of the loop function is the integral is not dropped. But he used very specific form of the potential V, and also we used, which is more important, a non-relativistic treatment for the meson baryon energies and momenta. And in his approach, when he considered only the Weinberg-Tomozawa term, he wrote the potential in this form with this central piece that includes the off-shell momenta, and it is equivalent to the on-shell form, which is standardly written like that. And then he fitted the parameters, and the result was that we have only one pole when we use this potential, and 2 poles when we do not drop, when we drop the off-shell effects and use the on-shell form. However, we put this approach under the scrutiny together with Peter Bruns recently, and we were able to rewrite the algebraic symmetric solution in a form where we introduced the effective potential that reduced this to the on-shell version with one neglects the contributions of tadpole integrals. So the potential effective is then written like that, and you can see that it has contributions which are represented by integrals I0 and I1, and these are really tadpole integrals that contain the off-shell effects. And if these are dropped, we are left with the on-shell interaction only in the potential. And so in this form, the on-shell approximation is quite transparent. It's just equivalent to neglecting the integrals IN. And we were also able in this approach to write the amplitude by János Révay in a form that shows that this amplitude does not vanish in the threshold, at the threshold, when the quark masses or the meson masses go to 0. So if the on-shell approximation is performed, the tadpole integrals are equal to 0, and then the scattering matrix, which we were able to explain in this form, really goes to 0 as it should. But if the off-shell effects are accounted for, then this amplitude does not go to 0 at threshold. And so the approach by János Révay violates the chiral symmetry. And the origin of this violation can be really traced to his use of non-relativistic kinematics. And a proper relativistic treatment is possible, as we were able to show, and then we again get some effective potential, which includes some contributions from tadpole integrals, and it's best shown in the figure, I believe, in which we show the energy dependence of the effective potentials. Here by dotted line, you see the Weinberg-Tomozawa term, classically on shell, and the blue line is the effective potential treated relativistically when the off-shell effects are treated properly relativistically. So you see there is not a big difference between this potential, Weinberg-Tomozawa potential, and the relativistic potentials, including the off-shell effects. But when we use non-relativistic approximation, as János Révay did, you get the energy dependence of the potential, which is pretty off. So it's not that surprising then this non-relativistic potential then violates the chiral symmetry. So we were happy to get the 2 poles when we introduce the relativistic kinematics. Okay, but the pole positions were not quite where we would like them to be, and I have not much time to discuss this. I would also just like to say that the last year there appeared quite extensive analysis of experimental data by Anisovic and collaborators, and that they did partial wave analysis of low energy data on chi- proton and pi sigma interactions. I show here this large set of experimental data they covered, and they ended up with 2 equivalent solutions. One of them was 1 pole, and the other one was 2 pole. And the 1 pole solution they were able to identify as U3 singlet, and the 2 pole solutions as singlet and octet, both compatible with predictions by Gido and others. So from this, we can get that looking at the experimental data, it's really difficult to distinguish the 2 poles in lambda 1405. But this is the partial wave analysis, and one should look also at cross sections of some specific reactions, and then maybe as some people do already, and maybe then the two-pole structure can be seen better. And finally, I would like to mention our new model, which we developed together with Peter Bruns. This is again based on effective chiral Lagrangian, this time manifestly Lorentz invariant. The previous Prague model used Lagrangian that was formulated with heavy baryons. And in addition to our previous fits, we now also include the eta lambda and the eta sigma 0 cross sections to cover the lambda 1670 region to have a better reproduction of this other resonance. We get quite good quality of the experimental fit of the experimental data, and here you can see the new pole positions in the isoscalar sector. And when compared with our older Prague model, which did not have this data, experimental data included, you can see that now the lambda 1405 poles are about one half distance from the real axis. And we have now also quite good reproduction of the lambda 1670 pole, unlike in the previous case. And in these figures, I show you how we reproduce the new experiment, the newly included data on the eta lambda and eta sigma cross sections. By blue line, I show the results. Now we have with the new Prague model, and the red dashed line shows the results by the previous Prague model. But at that time, as I said, we did not fit this experimental data. So it's not surprising that they do not reproduce them. In the bottom figures, in the left and right, you see the real and imaginary part of the K-bar and amplitudes with our new model in blue lines and compared with the previous Prague model. And I also put here the curves for the Kyoto Minhid model by Ikeda, Hyodo, and Weise. And you can see that our new model almost coincides concerning the predictions for chi-minus proton amplitudes with the Kyoto Minhid model. And it's a bit surprising because there are some differences in the two approaches. So I think it's more a coincidence. Especially we treat the Born terms differently in our approach. And also, as far as I remember, they did not fit this experimental data. So this is more coincidence that the real physics that these two similar amplitudes. And with our new model, we also would like to look in more detail on SU3 flavor structure of the poles, which are assigned to lambda 1405 and lambda 1670. And then when we are close to the pole position, the amplitude can be approximated like that when we introduce the couplings to the different channels. And these couplings can be obtained as a residue of the amplitudes at the pole position. And in the isoscalar sectors, we can make from the SU3 flavor limit some predictions for the rates of these couplings. So at the SU3 flavor limit, then we have the singlet state. We have 2 octets, 2 decouplets, and 2070 plet, but the decouplets are not realized in the sector we are interested in with strangeness -1 and charge equals 0, and the 2070 plet does not provide attractive interaction. So in reality, if we want to have look at the position of the poles in the SU3 flavor limit, where they would generate any bound state or something like that, then we should consider only singlet at 2 octet states. And the questions are how are the lambda 1405 and lambda 70 poles related to these poles and existing in the SU3 flavor limit. And there is also a question, it is really possible to extract the flavor structure of this lambda excited state from the data observed in the physical limit where the flavor symmetry is broken? And the answer is provided in this table. We were able to follow the movements of poles in a similar way as Guido and others did almost 20 years ago, and we did so by scaling the hadron masses, meson decay constants, and loop function regulators when going from the physical limit in which the scaling factor was set to 1 to the SU3 flavor limit in which the scaling factor was set to 0. And here you can see the position of the pi sigma related pole and k bar n related pole in the physical limit. And this rate of the couplings, and this is for x equals 0 in the SU3 flavor limit. And these numbers for which we obtained in the SU3 flavor limit for the rates of the couplings of these channels to the poles, we were able to compare with the predictions for the singlet and octet states. And we can really confirm that the pi sigma related pole goes to the singlet state and k bar n related pole goes to the octet state in the SU3 flavor limit. And I can also tell you that the K cascade related pole seems to go to the other SU3 octet states. So not to the same octet state as the K bar n related state. But our analysis is not quite conclusive yet. We should really put still some work in it. And the rates in the physical limit, you can see they are quite different in some cases from the rates in the SU3 flavor limit. So we see quite strong SU3 flavor breaking, and from this I would say that when we look at the poles by fitting the experimental data in the physical limit, it's really hard to make any predictions about whether this state is related to SU3 flavor singlet or octet, as Anisovic and the collaborators did, because one really has to follow the path and the movement of the poles is into the SU3 flavor limit to do so. But anyway, it's very appealing and idea that we have 3 poles in the 0 coupling limits, and we have 3 poles in the SU3 flavor limit. And so where the poles are moved into physical states, we should have in the physical limit 3 states. And one of them is lambda 1670. And so where are the other 2 states? There must be both assigned to lambda 1405. And this gives me the belief that they are really 2 lambda 1405 poles as predicted in the chiral models. And the origin of the poles can be tracked to the non-zero interchannel couplings. We also scrutinized the suggestion by János Révai, which was, I think, worth the effort, and it was a good idea of him. But when introducing proper relativistic treatment, we are back with the 2 poles in the pi sigma k bar n coupled channel sector, and it is really tempting to connect the 3 SU3 flavored symmetric states, singlet at 2 octets with 3 lambda start states in the physical limit, providing 2 state poles for lambda 1405. But unfortunately, as far as I know, the available experimental data can be reproduced about equally well by models with just 1 pole or 2 poles. So we still lack a proper experimental proof of the 2-pole structure of lambda 1405. In the end, I would like to thank to Peter Bruns as my collaborator and colleague, and also you to your attention.